Hi, good morning. Thank you for watching. Here we're going to start another day of the Siintec, our international symposium at Siintec. And today we have a guest called Dr. Vito Francioso. He has a bachelor degree, a master's degree in construction engineering from Politecnico di Torino, Italy. During the last year of his MS program, he studied at Universidade de Coruña, Spain. In 2018, he joined the Viii research group at Purdue University, and in May 2022, he obtained his PhD in civil engineering. Vito was the recipient of the Buildland Dissertation Fellowship in 2021 and the College of Engineering Outstanding Graduate Research Award in 2022, among others recognitions. Currently, he has a postdoc at Purdue University. His research focused on unveiling a fundamental understanding of using construction and industrial waste materials in cementitious composites at a dimensional and temporal multiscale level. His goal is to develop new methodologies to design sustainable building materials with a holistic approach that comprises reduction of depletion of natural resource and valorization of waste, enhancement of durability and service life, and creating materials with beneficial proactive effects during service life. He aims to develop innovative materials for future built environments and engineered systems focused on sustainability. During his studies at Purdue, he has also served as a teaching assistant for 3 semesters, 2 of them in civil engineering materials course and 1 in a mechanical engineering design course. He's a former member of the Civil Engineering Graduate Advisory Council and has volunteered to help undergrad students prepare for ASCE competitions and organize different events on campus. Additionally, he has mentored several undergrad students, most belonging to minority groups, via the Summer Undergrad Research Fellowship and Office of Undergrad Research Programs. As a future faculty member, he feels a responsibility to encourage students of all genders and backgrounds to work in the STEM disciplines. So there's the little resume of our guest today. I thank you for watching at home, and thank you for the students and faculty members that are here. And thank you, Vito, for having the time to explain his research. So, Vito, thank you. Oh, we can't hear you.
See me or can you hear me?
Yes, now, thank you.
Yes.
Thank you for having the time. So we're going to start his presentation.
Bom dia.
Yeah, bom dia.
Are you going to share the screen?
Share just a sec.
Yeah.
If you want to add something to your about your experience, if you want to add something about your experience.
You said too much. You said too much. I just wanted to thank you for inviting me to this symposium. I think it's an honor for me, and I'm looking forward to a discussion with your students. So please, during my presentation, let me know. You feel free to interrupt me anytime if you have questions. Luara will translate if there is some, if we don't understand each other with the languages. So whenever you want me to start, I can start. Let me know if you can hear me well and if you can see the screen.
Watching on YouTube, if you want to ask some questions, just type it out and I'm going to read it here. You can also ask it in Portuguese and I can translate the question and the answer. So you can start. Thank you.
Yes. Okay, I will start. Let me know if there are any issues. All right. Good morning, everyone. Bon dia. I'm Vito Francioso. I'm actually a postdoc, currently a postdoc at Purdue University. I will just start with my presentation, where I already said too many things about me. So this is the title of my presentation, Reutilization of Sugarcane Bagasse and Recycled Aggregate in the Concrete Industry. Of course, there is no much time to talk about everything that I did during my PhD. I will just talk about 3 studies, but let me know, interrupt me anytime, ask me question if something is not clear. So this is the outline for the presentation of today. I will be giving a brief introduction, and then we will see the utilization of sugarcane bagassiage, and then recycled aggregate, recycled plastics, and recycled concrete aggregate, and then some final remarks. So cementitious materials in our social and economic development are indispensable. Concrete is perhaps the most eco-friendly, versatile, low-cost, and durable construction material. Its embodied carbon is 10 to 20 times lower than that of glass and steel. So where does the environmental impact come from? Well, with over 30 billion tons of global annual production, concrete is the most used artificial material in the world. Concrete is a composite material made mixing together cement, water, and aggregate. A significant contribution to the impact that the construction sector has on the environment is due to the cement industry. In fact, the production of cement is responsible for the 8% of the global CO2 emissions. And this comes from the fuel necessary for the production of the clinker, for the calcium carbonate decomposition, and also for the transport. Besides cement, aggregates have a great impact on the sustainability of construction, since they represent around 60 to 70% of the volume of the concrete. Each year, approximately 8 billion metric cubes of aggregates are used in constructions, and the majority of them come from raw materials, consequently contributing to the depletion of natural resources. Now, there are different approaches to reduce the environmental impact of cementitious materials. One approach is reducing the cement content, for instance, substituting it with supplementary cementitious materials. SCMs are natural materials or industry byproducts used as admixtures in concrete to make up part of the cementitious component. Another approach is replacing natural aggregate with recycled aggregates, such as recycled concrete aggregate and recycled plastic, which can contribute to reducing both the natural abiotic depletion and waste generation. Furthermore, we could improve the sustainability of the cementitious composite, enhancing their durability and providing the material advanced properties that may have a positive proactive effect during service life. For example, titanium dioxide nanoparticles have been found to provide cementitious composites with photocatalytic properties that may reduce different pollutants concentration from the environment while enhancing their strength. I won't be able to talk about the titanium dioxide today, but we have used it in many of our studies, and we have used it in conjunction with recycled concrete aggregate as well. So we have seen that there exist different approaches, but how do they work synergistically? For example, if I replace natural aggregate with a recycled aggregate, how will their performance change? These slides summarize the studies that I will be presenting today. I will discuss first the utilization of sugarcane bagassiage and how curing temperature can change the environmental impact in mortars. Then I will be assessing the impact of recycled plastics on the high temperature resistance of mortars. And finally, I will evaluate the influence of the ambient condition on the thermal conductivity of composites that contains recycled concrete aggregates. For each of these studies, I will make a brief introduction and then explain my motivation and providing my hypothesis for the studies. So let's start with the first studies, the influence of curing temperature on the life cycle assessment of sugarcane bagassiage as a partial replacement of cement in mortars. This research has been submitted in a paper this month, so it's very fresh. Now, currently, one of the most used supplementary cementitious materials is coal fly ash, a byproduct generated in power plants. However, fly ash may become a limited resources due to the dismantling of coal-based power plants in developed countries. Thus, there is a need to find new products that can replace the fly ash in concrete production to lower the amount of cement and its corresponding CO2 emissions. Recent attention has been shifted to the utilization of sugarcane of biomass ashes. An example of these biomass ashes is sugarcane bagasse ash, which is a biomass waste resulting from sugarcane bagasse combustion for electricity production. Sugarcane bagasse is a byproduct of the sugarcane industry in sugar and ethanol production. More than 50% of the countries are involved with the sugarcane crops, totaling an annual global production of about 2 million metric tons, with Brazil being the world's undisputed leader with 757 million tons of sugarcane production in 2020, followed by India, 370 million tons, and China. Now, as the production increases, the amount of the ashes generated will also increase, contributing to the ongoing issue of biomass waste management. These ashes are often disposed of in landfills without any regulation and control. However, research has demonstrated that they can be used as a partial cement replacement for the production of mortars and concrete with acceptable strength and durability, which may also increase the sustainability. Previous studies show that curing temperature influences the effect that biomass ashes have on compressive strength of cementitious composites. If the temperature changes the effect of these ashes on strength, the cement content needed to achieve a given performance will also change. Then, what are the real savings of using bagasse ash, of biomass ash, in terms of cement reduction as a function of the curing temperature, right? We need to compare the samples with the same performance to make a fair comparison. So we realized that no studies evaluated before the impact of the temperature, the effect of the curing temperature on the environmental footprint of using bagasse ashes on cementitious composite. So the objective for this research was to study the influence of curing temperature on the sustainability of sugarcane bagasse ash as a partial replacement of cement in mortars. My hypothesis is that the curing temperature is a critical factor that determines the environmental footprint of sugarcane bagasse ash utilization as a partial replacement in cementitious composite production. For these studies, I designed 3 mixtures: a reference mixture without sugarcane bagasse ash, and 2 mortars with 10 and 20% replacement of cement with sugarcane bagasse ash. These percentages replacement were based on previous research, while the curing temperature chosen were 21 degrees Celsius and 45 degrees Celsius. For the experimental campaign, I performed compressive strength tests, physical and chemical characterization of the ashes, and finally, a life cycle assessment. Results show that the replacement of cement with sugarcane bagasse ash at standard curing temperature, so at 21 degrees Celsius, had a slightly negative effect on the compressive strength. Nevertheless, the difference compared to the reference mortar cured at the same temperature was lower than 8% in both cases, in both replacement, 10 and 20%. However, when the samples were cured at a higher temperature, the mortars with sugarcane bagasse ash exhibited an increase in compressive strength, over 20% in both cases compared to the plain mortar cured at the same temperature. Thus, the results suggest that the curing temperature modifies the effect of sugarcane bagasse ash on the mortar's compressive strength. Therefore, from here, I performed a secondary experimental campaign to estimate the variation of cement content required to obtain a compressive strength equal to the compressive strength of the reference mortar without sugarcane bagasse ash, depending on the sugarcane of the ashes replacement. The results of this additional experimental campaign contributed as an input for the life cycle assessment. What is a life cycle assessment? LCA is a tool for evaluating the environmental impact associated with a product system throughout its life cycle, and it can be divided in 4 steps. The first step, we see it here, is the goal and scope definition. The scope of this life cycle assessment was to quantify how curing temperature affects the environmental performance of eco-mortars with different percentages of sugarcane bagasse ash. The system boundary that I chose for this study was cradle to gate, so from the production to the material to the point that the material is then sold. And the functional unit for the functional unit that I chose for this study was 1 cubic meter of mortar with the same compressive strength as the reference mixture. So the mixture with plain Portland cement and without ashes, and cured at the same curing temperature. The second step in the life cycle assessment is the life cycle inventory. In this stage, input and output data must be identified and allocated for each material production. To help with this, numerous databases have been developed which provide essential inventory data representing the average production and supply condition for products and services. The third phase of the life cycle assessment is the life cycle inventory assessment, which is crucial to assess the total environmental impact of the investigated mortars. The life cycle impacts were assessed by analyzing nine environmental impact categories showed on the right here of the screen. Now, the last phase of the LCA is the interpretation of the results obtained for the impact assessment. For these studies, I followed two different approaches. I analyzed the single impact categories, and I also I use a normalization factors to obtain a single unified index with comprises all impact categories. As showed before, the life cycle assessment considered 9 different environmental impact categories, which are displayed here in the graphs. For all of them, the substitution of cement with sugarcane bagasse ash reduces the impact. Furthermore, as can be observed here, the higher the curing temperature, so we are observing the graph on the right, the higher the curing temperature, the higher curing temperature, significantly reducing the environmental impact. Among these, waste generation was the only one that was not affected by the curing temperature. The results show that a replacement of about 100 kilograms of cement with sugarcane bagasse ash per cubic meter of mortar produces over 2 times higher reduction in the environmental impacts when the curing temperature is 45 degrees, so higher curing temperature than when the curing temperature is lower. The results can also be represented with a single normalized unified index, which accounts for all the impact categories in a single score that is then normalized to its reference. So to do this, we use the normalization factors. These normalization factors put each environmental impact in relation to the impacts of society's production and consumption activities. So again, the result clearly showed that the curing temperature is critical when assessing the environmental impact of mortars containing sugarcane bagasse ash. In the case of 20% replacement, the reduction compared to the reference mortar was 14% at 21 degrees and 31% at 45 degrees, so more than the double. Then we can conclude that the reduction of the environmental impact when using sugarcane bagasse ash as a partial replacement for cement highly depends on the curing temperature. When mortars were cured at 45 degrees Celsius, the use of sugarcane bagasse ash reduced the environmental impact of mortars 2 times with respect to the reduction at 21 degrees Celsius. And then the sustainability of sugarcane bagasse ash utilization as a partial replacement of cement will be higher when the mortar is poured in hot region or during days with higher temperature. Therefore, the external curing temperature is an important factor that should be considered when the sustainability of cementitious composites containing sugarcane bagasse ash, but also other biomass ashes, is assessed. Now, let's see some utilization of recycled plastic in cementitious composites, in cementitious materials. This research has been published in the Construction and Building Material Journal in 2021. Previous studies have shown that the performance of cementitious composites reinforced with plastic fibers can be enhanced, including its mechanical properties and durability. Excuse me. The plastic fibers can act as a reinforcement and produce a bridging force that across the cracks that prevents their propagation. Because of these fibers bridging cracks in the matrix, the fiber-reinforced mortars may exhibit significantly higher flexural strength than plain mortar. Furthermore, compared to other options such as steel fibers, plastic fibers have a lower carbon footprint, are cost-effective and corrosion-resistant. However, the effect on the strength has been reported to be contradictory. It's been observed that the interfacial transition zone, the ITZ, between the matrix and the plastic fibers is affected by the smooth surface and hydrophobic nature of the plastic, resulting in a poor anchoring. Several studies have demonstrated that the polypropylene fibers can prevent spalling failure of concrete under compressive loads caused by internal stresses when they are subjected to elevated temperature. However, the influence of elevated temperature on the flexural performance of recycled plastic fibers reinforced mortars and its effect on the interfacial transition zone between the matrix and the recycled fibers was not being deeply investigated. Moreover, no studies were found on the possible effects of the cooling processes on the residual strength of these eco-mortars. So the objective for this study was to analyze the impact of using recycled polypropylene fibers on the high temperature resistance of eco-mortars. My hypothesis is that the exposure to elevated temperature will affect the interfacial transition zone bonding between the matrix and the recycled fibers, and this will impact the residual strength of the eco-mortars once it's cooled down. For this study, I designed 4 mixtures: a reference one without any fibers, and 3 mortars with different percentage of recycled polypropylene fibers: 0.5%, 1%, and 2%. The flexural and compressive strength tests were performed at 28 days before and after exposure to elevated temperatures. Besides, digital image correlation (DIC) technique was adopted to study the evolution of crack propagation and strain distribution in the specimen during the 3-point bending test. And finally, the interfacial transition zone was inspected by means of a digital optical microscope. The samples were exposed to for 2 hours at 200 degrees Celsius, and then they were tested after 2 different cooling regimes: thermal shock, meaning that the samples were tested right after the 2 hours exposures, and then after 12 hours cooling in the oven. Now, the use of recycled polypropylene fibers did not significantly impact the flexural strength under standard condition, so the unexposed samples. The variation with respect to the flexural strength of the reference mortar is within 15%. However, as we can see in these other figures, when I'm representing the variation, of flexural strength after high temperature exposure compared to the strength under standard condition, the polypropylene fibers decrease the loss of flexural strength produced by a high temperature exposure and thermal shock. On the other hand, the slow cooling increased the flexural strength compared to the samples tested under standard condition. And this enhancement is specifically higher in samples with polypropylene fibers. Since the matrix is the same, these results suggest that the bonding between the fibers and the matrix was enhanced after the high temperature exposure of slow cooling. Even though the recycled fibers did not remarkably affect the flexural strength, they have been found to increase the maximum strain before ultimate failure and provided the composite material a secondary flexural strength. So to evaluate the influence of exposure on the fibers bonding, I analyzed this secondary strength. Since this strength is only related to the amount of fibers and the bonding between the fibers and the matrix. As we can see from figure 26, which presents the secondary strength of mortars before and after exposure, the higher the percentage of the fibers up to 1.5%, the higher the secondary strength. The thermal shock, which is the red curve, reduced this secondary strength with respect to the normal condition. And this can be related to the fact that the thermal shock samples were tested in hot conditions, affecting the mechanical properties of the fibers. Nevertheless, in samples tested after slow cooling, the fibers could recover all their strength and contribute again to the strength of the composite. Not only that, it improved, suggesting an improvement in the fiber matrix bond. These pictures show how high temperature exposure affected the interfission transition zone between the mortar and the recycled polypropylene fibers. For the unexposed sample on the left, the optical microscope revealed a clear and well-defined interface between the mortar matrix and the fibers, whereas in the case of 200 degrees Celsius exposure, the image on the right, the fibers penetrated the pores of the mortar matrix, enhancing the adhesion between the fibers and the mortar matrix, and consequently increasing the flexural strength and secondary strength as observed before. So we can then conclude that the recycled polypropylene fibers have a negligible effect on the mortar flexural strength under standard conditions. However, they increase the maximum strain before failure and provide the composite material a secondary flexural strength. The addition of recycled polypropylene fibers mitigate the flexural strength loss caused by high temperature exposure and thermal shock. The secondary flexural strength might be lower at high temperature than at standard condition. However, when the recycled polypropylene fibers reinforced mortar is completely cooled down, the secondary strength will be higher. And finally, after 200 degrees Celsius temperature exposure, for 2 hours, the polypropylene fibers can penetrate the pore network, enhancing the adhesion between the fibers and the mortar matrix after they are cooled down. Finally, we are going to see the effect of recycled concrete aggregate on the mortar's thermal conductivity susceptibility to ambient conditions. This research has also been published in the Journal of Building Engineering in 2021. Now, the building and construction sector is responsible for 39% of the global energy-related carbon emissions. 28% of this comes from the building operation, HVAC, and power. Therefore, enhancing the thermal insulation capacity of cementitious composites used in building construction might reduce the energy consumption of building during their service life. It is known that the thermal conductivity can be reduced by replacing natural aggregate with recycled concrete aggregate, which have a lower thermal conductivity. However, no research was found on the effect of the recycled concrete aggregate on the susceptibility of the thermal conductivity to saturation degree and ambient temperature. Why it is important? It is important because understanding these effects is crucial to assess the actual environmental impact during the service life as a part of the building component. So the objective for this study was to assess the effect of recycled concrete aggregate on mortar's thermal conductivity susceptibility to ambient temperature and moisture content variation. The hypothesis is that the higher porosity due to the utilization of recycled concrete aggregate may change the susceptibility of thermal conductivity of the recycled composite exposed to different ambient temperature. Here I designed 4 mixtures with 0, 25, 50, and 100% of recycled concrete aggregate. However, only 3 of them were selected for the thermal conductivity, while for the assessing the thermal conductivity, while the other one, the 25% replacement, was used to validate the model that I will present later. So prismatic specimens were cast for flexural strength and compressive strength tests, and slab specimens were cast for thermal conductivity evaluation. A total of 135 thermal conductivity tests were performed here. Each sample was tested at 3 different ambient temperatures, 4, 20, 24, and 43 degrees Celsius as per the ReLAM standard. And also 5 different saturation degree were studied, from dry to fully saturated condition. The density and the permeable porosity were also determined, and finally I developed an equation. I designed an equation which allow to obtain the thermal conductivity as a function of different variables that we will see later. The figure 28 shows that the thermal conductivity as a function of the recycled concrete aggregate for each saturation level. The higher the recycled concrete aggregate replacement, the lower the thermal conductivity as expected. Also, the higher the saturation level, the higher the thermal conductivity. However, more importantly, if we observe the variation of thermal conductivity between the dry and saturated state, we see that the higher the permeable pore space, the higher the variation. So higher recycled concrete aggregate replacement, the higher will be the variation in thermal conductivity between the dry and the saturated state. Regarding the effect of ambient temperature, the most important result is that the higher the porosity, so the higher the recycled concrete aggregate content, the less susceptible is the recycled mortar to changes at higher ambient temperature. Also, we use a response surface method to study the combined effect of saturation degree and ambient temperature on the mortar's thermal conductivity. In these graphs, the point represents the experimental results, while the surface represents the estimation. As we can see, the thermal conductivity increases with both moisture content and temperature. However, the influence of saturation level of the moisture content is more important. The response surface method was also performed to assess the combined effect of recycled concrete aggregate in terms of permeable pore space and the saturation degree on thermal conductivity of mortars. Finally, based on the result from the response surface method analysis, where the thermal conductivity was evaluated as a function of porosity and saturation degree for each ambient temperature, I propose an equation that estimates the thermal conductivity of cement mortars as a function of the permeable porosity, saturation degree, and temperature. As shown in figure 34, a very good agreement was found between the numerical values and the experimental results. The two dotted lines represent an error of plus or minus 5%. Therefore, this proposed model is accurate and able to predict the thermal conductivity of cement mortars, knowing the amount of permeable porosity, saturation degree, and ambient temperature in the range of 4 to 43 degrees Celsius. The accuracy of this model was also validated through several additional tests where training data as well as arbitrary values of ambient temperature, saturation degree, and porosity were tested. And if you remember at the beginning, I said that with the 25% replacement of recycled concrete aggregate, we didn't use it for the thermal conductivity. We actually use those mixtures, those samples to validate this model, to validate this equation. So based on the results of this study, we can conclude that the variation in thermal conductivity strongly depends on the moisture content and the ambient temperature at which the thermal conductivity is calculated. Also, mortar with recycled aggregate, and such as, for example, higher porosity, presents less thermal conductivity variation to the changes in ambient temperature. And finally, the use of recycled concrete aggregate increases the mortar accessible porosity, which heightens the importance of the saturation degree on the thermal conductivity determination. The higher the porosity, the more susceptible is the mortar's thermal conductivity to changes in moisture content. Now, I came to the end of my presentation. I will summarize the main conclusion of these studies. So, the results of the first study on sugarcane bagasse clearly indicated the sustainability of sugarcane bagasse ash utilization as a partial replacement for cement, but also this is true for other biomass ashes, will be higher when mortar is poured in hot regions or during days where there is high temperature. Therefore, the external curing temperature is an important factor that should be considered when the sustainability of cementitious composites containing biomass ash is assessed. As we have seen at higher temperature, at 45 degrees Celsius, the use of sugarcane bagasse ash reduced the environmental impact of mortars 2 times with respect to the reduction of standard curing temperature. Also, the recycled polypropylene fibers, even though they have a negligible effect on the mortar fractional strength under standard condition, so no exposure to high temperature, the exposure to after exposure to high temperature and cooling, the polypropylene fibers increase the fractional strength as well as they decrease the loss of fractional strength in samples after thermal shock. And this can be explained as the enhancement of the bond. Finally, the use of recycled concrete aggregate increases the mortar accessible porosity, and the higher the porosity, the more susceptible the mortar's thermal conductivity will be to changes in moisture content. Thus, special attention to the variability of the thermal conductivity due to the saturation degree should be taken when evaluating the thermal performance of mortars with recycled concrete aggregate. And also an equation that accurately estimates the thermal conductivity with an error less than 5% of cement mortar as a function of the thermal porosity, saturation degree, and ambient temperature was proposed and validated in one of our studies. And to conclude, I want to acknowledge the other co-authors of the studies that I presented here. My advisor, Professor Dr. Miriam Velisancos, my colleague Carlos Moro, and also there is a typo here. The one on the right is Alberto and then Marina. These are my references, and this concludes my presentation. Please, if you have any question, I know I was very fast, but I would be very happy to answer all your questions.
Can you hear me?
Yes, I can.
Yes. So thank you so much for your presentation, and I want to know if someone has any questions besides Professor Moisés. He has a question, but I have a question first. Related to the sugarcane bagasse ash.
Mm-hmm.
Just a sec.
Yeah.
Yeah. No, some students wanted to come in the room. So related to about the sugarcane bagasse ash,
Mm-hmm.
you said you need a higher temperature for the curing. When you studied the life cycle, you did the life cycle assessment, did you consider, I don't know, the fuel and the energy that you needed to use this higher temperature?
Mm-hmm. So in our life cycle assessment, I did not consider that because what we are stating here is that when you are pouring the concrete or the mortars where the high temperature is where the ambient temperature is high or higher than the standard, that will improve the performance of your cementitious composites. So that for sure is something that should be done. I mean, if you, let's say we are precasting some elements and then we are curing them at higher temperature to improve their performance, then it makes sense to we should account for the energy that we need to heat the samples in the life cycle assessment. But for this study, we wanted to demonstrate that when the temperature is higher, the effect of the sugarcane bagasse ash replacement will be higher, will be better. And this is true also for other biomass ashes.
Okay, thank you. I give you the mic, someone else.
Professor Vito, first of all, congrats on your presentation.
Thank you.
My name is Moisés. I'm professor of civil engineering here in Siintec. As we can see, when we use fibers inside polymers composite, when exposed to higher temperatures, the strength, the compressive strength and flexor strength tend to reduce. In my thesis dissertation, I worked with natural fibers inside polymers composites, and I worked with the durability of these fibers inside with this hygrothermal environment. And one of the things that we have found is something that about the treatment of these fibers. We have found many articles that they are working with this topic to find the best treatment that can be used to some specific fibers. In my case, for these sisal fibers that I have worked, we use ionic liquids as a treatment. My question is about these polymers fibers that you have worked in your article. Have you seen about what kind of treatment that can be used to enhance or to maintain this strength, resistance, or flexor strength? Yeah, I would like to know more about this about the treatment that can be used to maintain this resistance in something else.
Yes, thank you, Professor Moises, for your question. This is actually a very important topic because, as we know, the durability is extremely important. And in our case, for our polypropylene fibers, we didn't use any treatments because we wanted to use them as they came. Because they are recycled fibers. They come from the hay industry, and so they ship them to us. This is a company, is a very small company that recycles the how can I say the the um, the laces where they tie the hay, and so they don't know what to do. It's a waste, so they just came up with this idea, and they shredded them into fibers, and they are selling them for application of pavements or in concrete. So I'm also aware that there are many treatments. There are several types of fibers, and you can do many treatments. But for our study, for our fibers, we didn't use any treatment. We wanted to use that waste as it was. For example, one issue with the plastic fibers is, as I said during the presentation, that they are hydrophobic, right? So they don't absorb water. While, for example, if you are using natural fibers, they will absorb water too. So you need to take into account also the amount of water that in the mixed design, you need to account of the amount of water that you need to add more, because those fibers are absorbing the water. There are chemical processes, chemical treatments for the fibers, physical treatments. It's for sure is very interesting, and um, there is there is more research to be done on the topic. And there are many fibers and many processes, and the problem when you use recycled concrete aggregate or recycled fibers or other fibers is, as you said, the durability. So if we can improve that, we will improve also the performance of our cementitious composites.
Perfect. Professor, this is very important because when you use this kind of treatment, you can modify the raw surface of these fibers and then enhance the adhesion, the bonds adhesion between the matrix and the fiber. But another question is about the length and the diameter of the fiber that you have used in your article. Can you tell me more about the length and the diameter? Because it influences a lot and how the composite will performs. And yeah, this is the question.
Yes. So the for the length, the diameter was the same for all the fibers. Now I don't remember. It was I think it was 1 millimeter, and then the diameter. Well, the diameter, they were rectangular fibers. So it was the you know was the length, like the depth of the fibers. So that was 1 millimeter, and then for the length we had variable lengths. I don't remember if I have a. Let me see if I can find a picture. So for the length varied from 1 millimeter to 1 centimeter. Let's see. No, I don't have it here. So here we have a scale of 0.1 millimeter. So this was, as I said, was 1 millimeter. The diameter, let's say the diameter was 1 millimeter, and then the length varied from 1 millimeter to 1.4 centimeter.
Thank you.
Let me see.
Yeah, we can see the picture. Any questions? Can you just check the YouTube if there is any questions on the channel? You know?
Also, Professor Moises, if I can add something on what you were saying before. For example, here, let me check. Let me put a little presentation. Can you see my screen?
Not yet.
Okay, can you see it now?
Yes, yes.
Okay, so the thing is, even though we didn't use any treatment for the fibers, what we observed here that when so the melting temperature of the fibers was 100, around 170 degrees Celsius, and that's why we chose the temperature of 200 degrees Celsius, because we didn't want to destroy our fibers. We just wanted to modify them. So when the samples were exposed to 200 degrees Celsius, the fibers started to melt, right? And so when melting, they started penetrating the pores. Now, if we test the samples in hot condition, the fibers are not contributing to the strength of the samples because they are in a melted state. But if we wait, so when the samples are, the material is cooled down, the sample is cooled down, the fibers can recover their strength because they solidify again, and in that way they have also penetrated the pores. So that's why the second strength was or the secondary strength was higher for the cooled samples than the standard samples. So in a certain way, this is a treatment of the fibers.
Thank you for explaining that. Is there any other questions? There's no questions on YouTube too, but so thank you so much, Dr. Francioso, for taking the time to come here and do this presentation, this lecture for us. We are leaving the streaming. It's on YouTube if you want to watch it later. And thank you so much for your time and for everyone for coming and watching.
Thank you very much for inviting me, and have a good day, everyone.
Thank you. Bye. Thank you, guys.